My name is Pranav Raj and this is my video for Lab 3. So in the situation that we looked at, a star is orbiting a black hole of unknown mass located at the origin. And based on my email address, a unique star trajectory was generated by a pre-existing program. Two key pieces of information that were given to us in the introduction that the star has a mass of 2 times 10 to the power of 30 kilograms and the time between data points in our trajectory is exactly 1 day. Now, similar to the process that we followed in the week 6 reading videos and the week 6 homework, I decided to follow the 4-step process. Number 1, identify the system, which is the star that orbits the black hole, and the black hole is located at the origin. Then we use observations to find the net force, and the observations were randomly generated for us by the pre-existing code. And then we specify interactions, specifically looking at the gravitational force of the black hole on the star. And for this, we'll look at the formula and how we implemented it in our code. And then finally, solve for unknowns, specifically the mass of the black hole. And in this lab, as there's no video recording or tracker portion, I'll be sharing my GlowScript code and then we'll go from there. Before we look at our GlowScript code, I wanted to talk about how we got an important statement. So starting off with our gravitational formula and then isolating M2, we get M2 is equal to the gravitational force times R squared over G times M1. And then we get that the mass of the black hole, or M2, is equal to F net, because remember, we said that the gravitational force is the only force that we're accounting for. So Fg is equal to F net. And then since the position of the black hole is at the origin, R squared is just the magnitude of the position of the star. So we don't need to account for the position of the black force squared. And then over G, our gravitational constant, times M1, or the mass of the star. So to summarize, we get that the mass of the black hole is equal to F net times the magnitude of the star's position squared over G times the mass of the star.
Exactly where we left off. This is the important statement that I just talked about how we got, which states that the mass of the black hole is equal to the magnitude of F net times the magnitude of the star's position squared over G times the mass of the star. And then we print the mass of our black hole at every time interval, and it should all be the same, as changes in the F net and changes in the mass star's position should balance out, leading to the same or very similar black hole mass. But again, quickly starting at the beginning of our code, here we see that we changed the seed to get our customized trajectory, and all the code here was pre-existing that sets up our trajectory and generates the observations that we need. Here, I changed the mass of the star to be 2 times 10 to the power of 30, and then delta t to be 1 day, or 86,400 seconds. And then here's the heart of our code, where we calculate P initial, P final, V initial, V final, using the simple concepts that we learned, such as P is equal to M times V. Then we calculate delta P and delta V. And then here we have our two most important statements. First, we calculate dp dt to be delta p over delta t, and then we state that F net is equal to dp dt, using Newton's second law, or the momentum principle, to say this. And then using the similar concept, we say that the parallel component of the net force is equal to the perpendicular parallel component of dp dt, and then the perpendicular component of net force is equal to the perpendicular component of dp dt. And this is very important, as it's important to understand that the parallel component of F net and the perpendicular component of F net are respectively equal to the parallel component of dp dt and the perpendicular component of dp dt. Like I said, using the F net that we just calculated, we are able to print out the mass of the black hole, and we'll look at the mass of the black hole next.
As we expected, all of our outputs are around 1.8 times 10 to the power of 34 kilograms, our final answer.
So, we mentioned that the parallel and perpendicular components of the rate of change of momentum and the net force are exactly the same. But when we think about it, they represent different things. dp/dt is the change of momentum over the change in time, while the net force is the sum of all the forces acting on our system. So as they represent different things, but they are exactly the same, it makes this such a crucial physics principle. Let's end with an interesting discussion. So, is it possible to find a value for the mass of the new black hole to be different from the mass we found for the original one if the motion of the star remains unchanged and is still affected only by the gravitational force of the new black hole? The simple answer, based on the formula that we looked at earlier in the video, would be no. If the mass of the black hole is changed, then the position of our star would not remain unchanged and would also change, as they are related, shown by the gravitational force formula.